In this learning objective, we're going to learn how to calculate delta G of a reaction by a different route. We're going to define what's called standard free energy of formation. Now, in thermal chemistry, you had learned about the delta H of formation. Here it's a delta G of formation. And we're going to use those values to calculate the free energy of a reaction. This equation looks very similar to one that you've seen before, but with G's instead of H's. So let's go through and look at this equation. First, it's standard state conditions. We see that little circle there, so that means we have 1 molar if it's solution and 1 atmosphere if they're gases. What these are defined as here are the free energy of formation. Now, the definition is very similar to the delta H of formation, but it's the free energy change that occurs when 1 mole of the compound is formed, okay, so it's going to be a product, and it's formed from the elements in their standard states. So that's the definition. And if you recall back to delta H as a formation, it's a very, very similar definition. Because of this definition, if you have a stable element, to make that element from itself doesn't require any energy, so the delta G of formation of any element is equal to 0. So now, we have that equation, and we can use that equation to calculate the delta G of a reaction. And we know that the delta G of a reaction, when it is less than, it's negative, less than 0, then it is spontaneous in the forward direction. So I want you to first of all calculate the delta G of this reaction and then determine if it is spontaneous as written. Well, the answer is yes, because the delta G of the reaction is a negative 818.0 kilojoules. If you did not obtain that value for the delta G of the reaction, go back and look. Number 1, did you incorporate the coefficient of 2 here? Yeah, you incorporate the coefficient of 2 here as well, but I didn't give you the delta G of formation of O2 because I expect you to know that it is 0. So it doesn't matter whether you multiply by 2 or not, because 0 times 2 is still 0. So it should be the carbon dioxide value and 2 times the H2O liquid value minus the delta G of formation of this. So minus a negative 50.8 to get up to that value of negative 818 kilojoules, and a negative value tells me that this reaction is spontaneous, as written. So we're going to learn another method for calculating the delta G of a reaction, and that is by utilizing various chemical reactions in which we know the delta G, and we can realize that the delta G of formation for an overall reaction is determined whether you can do it in one step or many steps. Okay, so if a reaction is the sum of various chemical reactions. So in other words, you can add up various reactions and come up with an overall reaction as the sum of those. Then the delta G for the overall reaction is simply the sum of the delta G of those various reactions. Now, you did something very similar with delta H's in what was called Hess's law in thermal chemistry. Very, very similar process, but we're going to see it played out here with delta G's. Let's see it done with this set of information. We're given delta G's for these 3 reactions. We know their delta G values, 1, 2, and 3. We are trying to obtain the delta G for this overall reaction that you see here. So if I could manipulate these 3 reactions below in such a way that they add up to give me that overall reaction, then I could add up their delta G values. So let's see if we can find the pieces that we need. We need CH4 gas on the left-hand side of the equation. This has CH4 gas, but it's on the right-hand side. So I'm going to reverse this reaction, and that would be CH4 gas producing carbon solid, which is graphite, plus 2 H2 gas. If you reverse the reaction, you would change the sign of the delta G. It would be a positive 50.5 kilojoules. Okay, so we have the first piece in place. We come to the second substance that we're trying to get into place, and that is Cl2. If I look down at these reactions, I see that Cl2 is in 2 of these reactions. And so I'm going to skip over the chlorine for now, and I'm going to go to the next substance. The next substance in line is the Cl4. Cl4 only appears in the second reaction here. See it here. And it's on the correct side of the equation. It's the correct quantity, so I'm going to bring that reaction down just as I see it. Carbon in the form of graphite plus 2 Cl2 gas produces CCl4 gas. Since I'm using the reaction exactly as I see it, I will use the delta G exactly as it's given. So now I have this in place. That gave me a couple of chlorines, which I need 4, but I only have 2 so far. So let's see what happens next. I need the next, look at the next substance. It's HCl gas. I need 4 moles of it. Down here is HCl gas, but there's only 2 moles of it. So I'm going to double that equation. That's going to give me 2H2 plus 2Cl2 generating 4 HCl, and that will give me a delta G for this reaction 2 times the size of the delta G of the reaction that was up there. So it's 2 times the negative 65.3 kilojoules. All right, now we want to see, do these reactions add up to give me the reaction I was looking for? Let's cancel out anything that's in common. I have 2H2 and 2H2. That gets canceled. I have carbon solid in the form of graphite. That gets canceled. Nothing else is canceled. The chlorines won't cancel because they're on the same side of the equation. And that will leave me with CH4 gas plus 4 Cl2 gas yielding CCl4 gas plus 4 HCl gas. That is indeed the reaction we were trying to obtain up here. They match. Therefore, I can take these equations that these delta G values that we see on the right-hand side, and we can add them together. And that will give me the delta G for this reaction. And the value is a negative 142.4 kilojoules. Very similar process to Hess's law. The last thing I want to talk about in this learning objective is why free energy is the energy free and available to do work. How come all of the energy is not available? Let's look at this reaction. In this reaction, the delta H is a negative 95.7. That is the enthalpy change, that is the heat given off. All of that is not available to do work. Why is that? If we look at this reaction, we see that we have 2 moles of gas going to 1 mole of gas. So the delta S of this reaction is going to be negative. It's less than 0. It's negative. For a reaction to be spontaneous, the delta S of the universe has to be positive. So I have got to have a positive delta S of the surroundings. It has to be greater than 0. I have to make up for the fact that the delta S of the reaction is negative. Now let's get some words up on the screen. So if the delta S of the reaction is less than 0, which it is here because I'm decreasing the moles of gas, then some of that energy, some of this energy here, released to the surroundings, has got to go to increasing the entropy of the surroundings. And we have to have at least as much, or a little bit more, actually, a little bit more delta S of surroundings being positive to overcome the fact that the delta S of the reaction was negative. So some of this heat has to be going out to the surroundings in order to bring up the entropy. So I'm not giving calculations here, but in this example, the minimum heat loss to the surroundings is going to have to be 33.4 kilojoules. I have to have that much in order to overcome the fact that the reaction was negative delta S. I have to increase the disorder by that amount. So this much heat is determined. Now, how do I know that much? Because we remember that the delta S of the surroundings is negative delta H over T. Now, some of that I want to be able to use as work. And the minimum work that I can get out of this would be 62.3, because I take the 33.4 out of this negative 95.7, and I can do 62.3 kilojoules of work. So this would be, in this case, the theoretical maximum. Erase that so you can read it. That would be the theoretical maximum amount of energy of that delta H that could be used, and that is the part that is free to do work. We are now at the end of our learning objective number 8. Our primary purpose of this learning objective is to learn new methods for calculating the delta G of a reaction. You had previously learned that delta G is equal to delta H minus T delta S. But here we learned about delta G's of formations and used them and summed them up to come up with a delta G of a reaction. And we also did a stepwise process where we added equations together to get the delta G of an overall reaction.